welcome to Ionic Bonding. Many of the things that we're going to talk about today we really have already touched on in other units, so a lot of this might sound like a bit of a review. An ionic bond is an attraction between a cation and an anion, a cation having a positive charge and an anion having a negative charge. The cation and the anion have formed because somebody lost an electron and somebody else gained an electron. So what really is happening in ionic bonding is we have a transfer of electrons. So it's kind of nice to look at this, pictorially to start. If we start with NaCl, Na's configuration is 281. In order to have our last number be 8, sodium's going to go ahead and lose that one electron, which works out really, really well because chlorine's last number is 7, which easily becomes an 8 by gaining that electron. So what happens here by losing one electron, sodium has +1 charge, and chlorine has a -1 charge. So one becomes a cation, one becomes an anion. So remember, this is our cation, and this is our anion. And now those two are attracted to each other and bonded together. It is nice to think about our total charge here, the fact that this has to add up to 0. So our net number of electrons has to equal our net number of protons. In the whole system, once they bonded, even though an electron moved, we didn't change our overall number of electrons. So the compound as a whole should be neutral. So we have a +1 for sodium and a -1 for chlorine. We check our total charge, 1 minus 1 is 0. So we have a nice neutral compound, just like we're supposed to. Now, ionic bonds this is a nice 1-to-1 ratio. Ionic bonds can form in a ratio that's not a 1-to-1 ratio. I believe there is a typo in your packet. This should really all say fluorine, so make sure that you have fluorine there. That's my bad. So in this case, calcium's trying to get rid of 2 valence electrons. So it's got to get rid of these guys right here. If fluorine is the only one that is available to bond with, the only element we have a situation where we have 7 valence electrons already. We can only fit 1 electron right there. So what's actually going to happen is a whole other fluorine is going to come along to accept that other electron. So this guy right here is going to end up going over there. So we actually had 1 electron go to 1 fluorine atom and 1 electron go to a different fluorine atom. Calcium lost 2 electrons and now has a +2 charge. And fluorine, each one gained 1, so each fluorine's charge is -1. When we talk about charge, we always talk about it for the individual species, not both of them combined. Our charge should still be neutral. We have +2 coming from calcium and -1s coming from each of the fluorines. And 2 minus our 2 negatives together is 0. So this does come out to be a nice neutral charge. So in an ionic bond, what's occurring is the metal is giving electrons to the nonmetal. This relates to the octet rule we talked about. By gaining and losing electrons, atoms can get 8 valence electrons, or that noble gas configuration that we want. This also relates to the concept of electronegativity when we talked about, effective nuclear charge, all that stuff. If you have a low electronegativity, like the metals, you're going to lose your electrons. High electronegativity, like the nonmetals, in an ionic bond you will be likely to gain. Another thing that's going to be really helpful in this unit is looking at something called the electronegativity difference. So if we actually can compare 2 pretty simple bonds here. So the bond in NaCl, which is an ionic compound. Na's electronegativity is 0.9. and Cl's is 3.2. If we subtract these 2 and calculate the electronegativity difference, which is really an absolute value kind of thing, they have a difference between them of 2.3. That's a pretty big difference when your whole scale is out of 4. Let's compare this to a carbon-oxygen bond. Carbon has an electronegativity of 2.6, and oxygen has an electronegativity of 3.4. If we subtract these two numbers, we get 0.8. That difference is very small out of that scale of 4. So what this actually tells me is a large electronegativity difference is more likely to be an ionic bond. Electrons are going to be transferred. Somebody's going to lose them, somebody's going to gain them, because their electronegativity differences the difference between their strengths is a lot. So the wimpy metal is going to lose. The higher electronegativity nonmetal is going to gain. The carbon-oxygen bond will actually be done by what we're going to talk about next, which is called covalent bonding. Covalent bonding is occurring there because it's kind of a more equal tug of war. So they actually will share instead of transferring. So some stuff to understand. Binary ionic compounds occur between two elements. So these are when we talked about just two capital letters, crisscross naming in the beginning of the year. This is a complete transfer of electrons occurring between a metal and a non-metal. Ternary ionic compounds are the same type of bonding. This is still a complete transfer of electrons. However, they're occurring between an element and a polyatomic ion. So if you think about, for example, sodium and nitrate, what actually happens here is one electron gets transferred from sodium to somewhere in that nitrate group. And we don't really care exactly where that is. We just need to know, hey, they're getting transferred and there's charges involved and we crisscross. This is going to involve two capital letters. This is going to involve 3 or more capital letters. But we still crisscross with both of them. It's just the use of table E, which makes it a little bit different. We do need to be able to draw ionic dot structures for compounds. So in order to do this, we're going to kind of think about that review we did where we talked about, regular Lewis structures versus drawing these for an ion. So sodium usually has 1 valence electron. Chlorine usually has 1, 2, 3, 4, 5, 6, 7. So what's going to happen is this guy's going to go here. So in my dot structure, I'm going to show that sodium lost an electron by that +1 charge and no dots. And chlorine has 8 valence electrons now because it's getting sodiums, therefore -1 charge. Some people like to show these. They kind of look a little neater if you kind of do something like that, but brackets aren't necessary, whichever one works. If you have a compound that's not bonded in a 1-to-1 ratio. So to show this graphically, I'm going to cheat for a minute, put 3 valence electrons on one side. I'll never do it again, I promise. And I'm going to put my 3 chlorines, which I know I have 3 of because of that guy right there. A little too close together. So what's happening here, we have one of these guys going here, one here, and one here. So what's going to happen when I want to just kind of write this more simply, my aluminum loses those 3 valence electrons and has a +3 charge. This is a really nice time to use a bracket because each of my chlorines now has 8 valence electrons. Each of my chlorines has that -1 charge. If I throw a bracket around this guy, I can put that -1 charge out there. I do need to show that there are 3 of them, which is just coming from the compound that they gave me. So I am going to toss a little 3 right there. Lithium nitrate, if you take a look at this one, my lithium, I have a total of 3 of these guys, 1 electron each. Sorry, a little moment there. So these 3 electrons, 5 valence electrons. Sorry about that. These 3 electrons are going to all be transferred over to my nitrogen. 1, 2, 3. What I'm going to end up with will be lithium with no dots, +1 charge for each of them, and there's 3, so I'm using the brackets. and my nitrogen now feels like it has 8, and I'm going to plot my -3 charge right out there. The charges are pretty easy to determine, remember, using your periodic table. So take a moment, try out magnesium oxide and calcium iodide, pause the video, and I'll put the answers up and you can check them out in a minute. Magnesium oxide, nice 1-to-1 ratio, no dots to magnesium, 8 dots on the oxygen, and you show their charges, which are easily findable and predictable from the periodic table, with or without brackets, doesn't matter. This one I am going to show with brackets, mainly because we have 2 iodines, makes it a little bit easier. Iodine will end up with 8 dots from gaining electrons, -1 charge for each iodine, and my little subscript 2. To summarize this process, of course I did not give myself a place to do this, there we go. To summarize this process, your metal will have no dots. You will show the metal's charge, and that'll be positive, and you'll find that in the periodic table. Your nonmetal will have 8 dots. You will show charge, which will be negative, and findable in the periodic table. You need to account for subscripts. Ionic compounds are going to form something called a crystalline arrangement. So this is kind of like that, what would you picture what salt looks like? That's because salt is an ionic compound. Ionic compounds have a rigid, repeating, kind of ordered structure that works really well for them because opposite charges are next to each other. So if you imagine that this was NaCl, these would be your little Na pluses, and these will be your Cl minuses. And that is in 3D, so behind these you'd actually have another layer that's offset so that positives and negatives are next to each other. And this arrangement works really, really well because there are lots of attractions between opposite charges. And that leads to stability. Also predicts the general properties that these compounds are going to have. So the major properties of ionic compounds is that they tend to be brittle. So even though there's a lot of strength in them and they can be very strong compounds in a way, if you were to actually hit this with a hammer right here, you're going to offset this crystal, okay? When you offset this crystal, you're now going to end up with a situation where you have repulsion. So by simply hitting this thing with a hammer, you disturb the crystal, and you might end up with like charges next to each other. However, they do have a high melting point. So in order to melt an ionic compound, it actually takes ridiculously high temperatures because there are attractions here and here and here and here. And in 3D, there are tons and tons of attractions. So there are lots of attractive forces that are then difficult to overcome. So it takes a lot of energy, therefore it's going to take a lot of energy to take this solid and melt it and allow those particles to move apart from one another. There's just a lot of intermolecular forces. As far as conducting, if we put one of these compounds into solution, what it's able to do is dissociate or break apart. Sorry, this should be able to break apart. I don't know why it's not. So these guys can actually kind of float away like this. So if we are able to melt this thing, we heat it up, or we put it into water, these particles now become mobile. When we melt these, they're actually molten, so that's not a typical thing that we do with them, but putting them into water and showing them conducting is pretty common. So what's actually going to happen here, and when we do this, we get mobile charged particles. Whenever there's electricity involved, there are mobile charged particles. There are electrons or some other charged particle flowing around. So technically, electricity is a flow of electrons, and charged particles, allow that to occur. So now that those guys can move around, they can conduct an electric current. Remember, aqueous is solution. Melted, we'd be in that liquid state, but again, that's molten. That's pretty hot, pretty uncommon in day-to-day lab stuff. If you were actually given a compound and I'm like, hey, is this ionic? You would try to smash it, and it would crumble. You would try to melt it, and it would be really, really hard to do. Maybe even impossible. We'll do a demo with that. You could put it, if you could melt it, you could test if it conducted, but you probably wouldn't want to handle it. You'd probably put it into solution. Regular distilled water will not conduct, but you put a little salt in there, and yes, it will conduct an electric current. If you're given a whole bunch of compounds and you have to actually determine if they are ionic or not, you do this using the same side, opposite sides of the staircase rule. So ionic compounds are going to be compounds coming from opposite sides of the staircase. So they are the ones before that we used crisscross for. So you'll just take your two fingers and you'll plop them on the elements in question and determine it. Keep in mind the weird hydrogen rule. Hydrogen, we like to pretend, is on the right. So I pretend it's right over here, right next to helium. So calcium chloride we'll start with. You put a finger on calcium, put a finger on chlorine. Opposite sides of the staircase, that is an ionic compound. So you can go ahead and circle that up. H2O. Remember, we're pretending H is right here. O, same side of the staircase. Therefore, that's a covalently bonded compound. It's not ionic. CO2. Same side of the staircase. Remember, staircase is right here, so those are falling on the same side of the staircase. Same side of the staircase is not ionic. Rubidium bromide, Rb, Br, wholly opposite sides of the staircase, Batman. That's going to be an ionic compound. So pause the video for a minute, check the rest of these, and I will circle these answers. So these would be your typical ionic compounds. They have to absolutely just be opposite sides of that staircase, keeping that hydrogen rule in mind. Keep in mind if you had a compound, for example, with a polyatomic ion. So calcium carbonate is a nice example to look at. This has a polyatomic ion from table E, so that tells us, yeah, it's going to be ionic. In terms of the elements involved, we can use the periodic table for this too. We have calcium, carbon, and oxygen. There are actually two bonds in this compound, or more than two, but there's a couple bonds in this compound, and some are ionic and some are covalent. This compound as a whole is considered ionic. It is opposite sides of the staircase, polyatomic ion, and it actually makes it an ionic compound.